As we have focused primarily on the air interface, I would like to provide now an overview about RF testing for LTE. Let's start first with the base station side, where you can use Rohde and Schwarz leading signal generator and signal analyzer solutions for. Conformance testing of an LTE-capable base station is captured in 3GPP technical specification 36.141 based on technical specification 36.104, where base station radio transmission and reception is described. Transmitter and receiver tests are defined as well as performance tests. These tests are performed using well-defined fixed reference channels (FRC) and so-called UTRA test models. Fixed reference channels are used testing the receiver of the base station. These receiver tests are, for example, reference sensitivity level, dynamic range, in-channel selectivity, adjacent channel selectivity, blocking, receiver spurious emissions, and receiver intermodulation. The transmitter of the eNode B is verified performing power measurements, checking output power dynamics, signal quality, unwanted emissions, transmitter spurious emissions, and intermodulation. Fixed reference channels as well as the UTRA test models are used for particular measurements, where for each measurement it is defined what model or channel to be used. Last but not least, the performance of the base station is evaluated for receiving the physical uplink shared channel, physical uplink control channel under different conditions, and checking the PREG detection probability and passing the detection requirements. Let's pick some measurements and have a closer look. Looking in detail at the modulation quality measurements. If the frequency error is larger than a few subcarrier, the demodulation might not work properly at the UE. The requirement to be passed is 0.5 parts per million plus 12 Hz within a subframe. The error vector magnitude is a well-known quality indicator for the signal. It shows the amount of distortion affecting the receiver to demodulate the signal properly. The limit is for QPSK modulation 17.5%, for 16 QAM 12%, and for 64 QAM 8%. Time alignment is a measurement related to MIMO technology. The delay between two signals transmitted via two antennas is measured and should not exceed 65 nanoseconds. Downlink reference signal power measurement is an important measurement which proves the power accuracy of the downlink reference signals. The UE relies on the reference signals and uses this one for channel estimation. The power level with which one the reference signals are transmitted is provided to the UE by system information. The level with which one the base station is transmitting needs to be in the range of plus minus 2.1 dB. Remember, in LTE there is no filter definition as in wideband CDMA with the root raised cosine filter. It is up to the design engineers to meet the in-channel and out-of-channel requirements. Smooth filtering would result in a good modulation quality, means a good error vector magnitude. But too smooth filtering would decrease out-of-channel performance, means not passing adjacent channel leakage power ratio, short RCLR, or spectrum emission mask, SEM, requirements. The RCLR measurement itself is performed in two steps. In case of LTE FDD, first the presence of another LTE signal with the same bandwidth is assumed, second a wideband CDMA signal is available. The general limits are shown for both cases in the display table. Based on the used and tested frequency band, additional requirements in form of lower tolerances might be valid. This would be signaled to UE via network signaling and needs to be verified during testing. Such tests can be performed using Rohde and Schwarz high-end signal analyzer FSQ, where the screenshot is taken from. One of the performance requirements defined in base station conformance testing is the PREG performance. Two things are verified with these tests. First, the probability of false detection, which should be equal or less than 0.1%. Further, the probability of detection the preamble, which should be at 99% for a defined signal-to-noise ratio. Testing is done for 2 or 4 receiving antennas using different fading profiles and values for the signal-to-noise ratio. For the two modes, normal and high-speed mode, different preambles in different combinations are used. Please keep the NCNS value, the second column in the second table, in mind. The NCS value is not directly set, instead it is translated to a NCS configuration value. This one is specified in the 3GPP technical specification 36.211, which defines physical channels and modulation. When using one of Rohde and Schwarz vector signal generators out of the SMX family or the baseband signal generator AMU, the configuration value is set accordingly as shown in the screenshot. With this we stop the short and high-level excursus on eNote B testing. Let's focus now on the terminal side. As for base station, RF and performance requirements are covered in technical specification from 3GPP. This is 36.521 part 1, which relies on 36.101 UE radio transmission and reception. TX and RX measurements as well as performance requirements are specified here. For performance, it is of course essential to check the demodulation of the physical downlink shared channel under different conditions, as this channel carries user data based on a specified fixed reference channel. The second major performance requirement is the demodulation of the control channels, means the physical control format indicator channel and the physical downlink control channel. These channels inform the UE about the schedule decisions. In case of signal quality, measurements like error vector magnitude and spectrum flatness are done. The tolerances for error vector magnitude are the same as for downlink, QPSK 17.5% and 16 QAM 12%. As 64 QAM is an optional modulation scheme in the uplink, the limit is not specified yet, but it is considered to follow here as well the definition in the downlink. The frequency error is defined as plus minus 0.1 part per million. Further, IQ component and IQ imbalance are measured. One new measurement specified with LTE is in-band emission. With the in-band emission measurement, the interference to non-allocated resource blocks is estimated. You can think of that in the uplink you have, for example, a 20 MHz channel equals to 100 resource blocks, and not all of those 100 resource blocks are assigned to UE. Let's assume 20 resource blocks are assigned. So with the in-band emission, we check the impact of our UE to the resource blocks which are not assigned for transmission. So this is a very important measurement to check our impact to our UE's transmission. The IQ component measurement, which I already mentioned, is also known as LO leakage or IQ offset. It's a measure of the carrier feed-through present in the signal. In difference to the downlink, where we do not use the DC subcarrier, in uplink all subcarriers are used for transmission. In fact, that translates to a frequency shift of 7.5 kHz as shown here in the graph. With this frequency shift, energy of the local oscillator will fall into the two central subcarrier. And this impact needs of course to be measured based on the output power. The relative limits are shown here in the table based on the used output power. Also in the uplink we need to measure the RCLR. As you can see here, we have same requirements like in the downlink for LTE FDD. First, we assume presence of an LTE signal with the same bandwidth, and as shown here in the graph, which would be the second part of the RCLR measurement, the presence of 2 or 3G signal. Different limits might apply here as shown. For example, for the ultra frequency band 1, the second limit would be reduced to 43 dB, which is a very challenging limit, and so the performance of the transmitter needs to verify it against these tolerance. Receiver characteristics is estimated by a throughput measurement. The throughput, based on a fixed reference channel, should be more than 95% and is measured of course for reference sensitivity level, adjacent channel selectivity, blocking characteristics. As you can imagine, the throughput is based on the counting of ACK and NACs in the uplink. So for those type of measurements, normally a call is required so that we get the ACK and NACs in the uplink, can count these ones, calculate a block error rate from those values, and based on the fixed reference channel, which we have set it up in a downlink, we can estimate the throughput, which should be, as I already said, higher than 95%.